Well, good afternoon, it's Charlie ZL2CTM. Well, just continuing on with this amplifier, just to recap, it's based on an amplifier from W6JL that he produced some years ago. So just this is, I understand, the circuit that he came up with at that particular time, using two IRF Z24Ns. So in keeping with his original design, I am going to use those two devices again, and then look at how the circuit was set up and give it a go. So what I want to do today in this particular video is just have a look at this biasing network up here. We're just going to look at one side here, noting that the other side is just a mirror image. So just want to look at reverse engineering that and doing it all from scratch, just to get a better understanding of what's going on and how you'd go about actually designing this from first principles. So that's what we're going to look at today. So just redrawing that circuit here, what we want to look at or work out is our value of what I'm going to call RB. That's in the network for the 5.1 volt Zener. So that's the Zener I'm going to use that I've got out of the junk box. That's a 1N4733A. It's a 1 volt Zener. We need to work out what our emitter resistor is going to be, notionally RE. What this combination here needs to be, which is our trim pot. Why I say it's a combination is all I've got, well, I've got quite a few 10K 10-term trim pots, which I want to use, but I need to knock that down to a lower value, just to make sure I'm not going to exceed any power dissipations. But at the end of the day, I'm trying to get a range here of 2.2 to 4 volts, which we'll talk about soon. Those two series 4148 diodes, and then we need to work out what I'm notionally going to call RC, our collector resistor. So at the end of the day, this whole circuit here, what we're trying to do is provide a biasing voltage range of 2 to 4 volts. And why 2 to 4 volts? If you go to the spec sheet for the IRF Z24N, there's something called a gate threshold voltage. And that says the gate threshold voltage from the spec sheet, there's a minimum of 2 and a maximum of 4. So somewhere between 2 and 4 volts, if you apply that to the gate, that particular device will start to conduct. So that's a design goal that I want to be able to get, i.e. from that trim pot pick off, 2 to 4 volts. So that's what I'm trying to achieve. Right, so just starting, first we'll work out the Zener side, or the base biasing network, and then we'll work on the right hand side. So that particular Zener there is a 1 watt Zener. So first I just want to make sure I'm not going to exceed the maximum current allowed through that. So we know that power equals volts times current. So I can say the I max equals power divided by voltage. So 1 watt divided by 5.1 volts gives us 196 milliamps. I'm notionally going to say that the current through this network here is going to be 10 milliamps. A portion, so 10 milliamps flowing through here, and then there'll be a small amount will go through here, which is the base current through the device, but for all intents and purposes that's so small, we'll say that it's 10 milliamps all the way through. So having said that, we can now say there from Ohm's law, if that's 13.8 volts, let me just get into the range, 13.8 volts there, so 13 minus 5.1 volts gives us the voltage here. The voltage there divided by the current through that device, we can then work out what the resistance is, which is exactly what we're seeing here. So 13.8 volts minus 5.1 divided by 10 milliamps gives us 870 ohms. I'm just going to round that up, just for the sake of it, up to 1 k ohms, up to the nearest, well, it's not necessarily the nearest standard value, but it's going to be on the safe side, and that's close enough. That'll give us slightly less than 10 milliamps, but that's fine. That's good enough for this thing here to be nicely biased in the reverse breakdown region. Right, so having said that, let's just have a look at this emitter resistor here. So right now we're going to work out the value for our emitter resistor here. So we know from our transistor biasing that the difference in voltage between the base and the emitter is 0.7 volts. So we can say that 5.1 volts minus 0.7 volts gives us the voltage across this particular device here. If we divide that by our current through it, we can work out what the resistance of that's going to be. So let's say first work out the voltage across it. So 5.1 volts minus 0.7 equals 4.4. And I'm going to say that the current through this part of the network here, so our emitter current, which is going to be approximately equal to our collector current, let's just notionally say that's 10 milliamps. I think that's going to be a nice good number there, and we shouldn't have any problems with exceeding the power dissipation for our downstream components. So now we can say that 4.4 volts, so in other words the voltage across that emitter resistor, divided by 10 milliamps gives us 440 ohms. So I'm going to round that up to 470, our nearest standard value. So just doubling back then, so if there's still 4.4 volts across it, because there is, divided by 470 ohms gives us 9.36 milliamps. So just going to use that for our downstream, what I'm calling downstream computations for the voltage drops across this component, or these components down there. And as we say here, it's approximately equal to our collector current. So again, just looking at the collector circuit, so we've got that little trim pot at the top there, we've got those two series diodes, and then what we're calling RC. Now, I've got a 10k ohm resistor there. I want to get that a little bit further down to the original 470 ohm resistor that was used. So I'm just going to throw a 510 ohm resistor in parallel. So 1 over 10, 510 plus 1 over 10,000 gives us a number, 1 over our total resistance. And that'll work out to be 485 ohms, so that's close enough. And then we can say then that the voltage drop that's going to appear across that combination will be 485 ohms times the current through it, so Ohm's law, gives us 4.5 volts. So that's good. I said that we wanted to have a range here of 2 to 4 volts. We've got a 4.5 volt range across there, so it's more than we need, but that's fine. This is a 10-term pot, so I've got it'll be nice and easy to make that adjustment. So that's fine, so let's leave it at that. I'm happy with that. Now if you go to the spec sheet for the 4148, there are some graphs there which you can see there that at 25 degrees C at 10 milliamps, the voltage, the junction voltage is going to be around 0.75 volts. So I've got two of those in series, so therefore the total voltage across those two diodes is going to be 2 times 0.75 or 1.5 volts. So we need that. And then, so now we're sort of working down now, so we can get to our final point where we can actually work out what our collector resistor is going to be. So we said there's 4.5 volts across that first trim pot combination. We want the minimum value to be 2 volts. We've got another 1.5 volts across those two diodes. So we can say there that the minimum voltage at this point is going to be 2 volts minus 1.5 volts, which is half a volt. So therefore, if that's the case, then we know that there's 9.36 milliamps approximately flowing through that. Then we can work out what the resistance needs to be. So 2 volts minus 1.5 gives us the voltage here, divided by the current through it gives us 53 ohms. I'm going to use 51 ohms. So now I've worked out all three of those values. We've worked out our RB, we've worked out RE, and we've also worked out RC, as well as this combination here to give us at least, or around about that sort of 2 to 4 volts. So I think we're looking pretty good. So the next step now, and what we've done over here, is we've put it on the old breadboard. So hopefully that's in view there. We can turn on our voltmeter and we can turn things on. So what we're seeing here at the moment is exactly that circuit, and I've also connected it up to the actual MOSFET itself, the RF, like I say, Z24N. So over here we've got the 3906 PNP transistor, we've got the Zener and its associated resistor there. You can see there RC, the two series diodes, and then the combination of that 10-term 10k trim pot in parallel with the 500 ohm odd resistor. And the output of that, which is the variable voltage, is then being applied to the gate of the MOSFET. and then in the drain of the MOSFET is this light bulb down here. So this light bulb is the load on that particular MOSFET just for testing. And up here on the multimeter, you can see the voltage that's being applied to the gate of the MOSFET. So if you recall, this particular MOSFET here, according to the spec sheet, is going to start to conduct. Well, that threshold is somewhere between 2 and 4 volts, which we can see there. So if I was to bring that slightly down, we can see it's starting to turn off. So it's turning off about 2.1 volts or 2 roughly, and it's fully off. Come back up again, and we can just start to see, just starting to conduct now. We can just see the filament starting to glow, and as we increase that biasing voltage, we're turning that particular MOSFET harder and harder on. So you recall for this particular amplifier, it's a class AB amplifier, so we're going to be having it down here somewhere, looking to have 125 milliamps quiescent current flowing through each MOSFET in the no signal state. And then as the RF signal comes in, that'll bias that harder and harder on, more current, and therefore more output power. So in terms of the actual design and the function, I'm happy with that. I'm happy that I'm not exceeding any of the power dissipation factors or maximum power ratings for the various devices, be it a diode or the resistors or the Zener, so I'm happy with that. And I'm happy that I'm providing a usable range of biasing voltage to the MOSFET. So I'm going to leave that as. The only other thing down here is a little LM317 circuit. That's going to be for this fan here, and that just allows me then just to set some cooling voltage for the heatsink. Just an old computer fan which I had lying around the junk box, so we'll look to use that, and just like I said, a little variable voltage there, just to drop the voltage down from 12 volts so it doesn't sound like a 747 on takeoff. Right, so the only other thing I wanted to touch on today was to have a quick look at that ferrite transformer. So if I was to turn that off, you can probably see the scope a little bit better. Let me just turn that meter off. Now, so you recall that I wanted to have a look at and explore the option or the potential for using a ferrite rod for both the input and the output transformers. I totally acknowledge this is unconventional and it's not recommended. However, I am conscious that sourcing a more suitable transformer, for example this binocular core transformer, can be difficult in some places, and New Zealand is no different from there. So I just want to give this a go. I want to see if I can actually make a half functioning amplifier using these ferrite rods. So that is the plan. This particular one here, I'm going to I'll score that and I'll break it into half. But at the moment, it's just set up as the whole rod. So what we're seeing on the screen there is the output. There's two transformers here, one using the rod, one using the binocular core. They are both 3 turns to 3 turns. So 3 turns on the primary and 3 turns on the secondary. The input voltage is 1 volt peak to peak. And I've got the output on the scope there on 0.5 volt for peak to peak. So we can see there that so 0.51. Yeah. So what I want to do there, so yeah, it's better. This at the moment is the ferrite rod transformer, and what I'm doing there, I'm varying the frequency from at this point 3 megahertz. So 3 megahertz is giving me roughly 1 full division, which is 0.5 volt. So remember, I'm putting in 1 volt peak to peak, and I'm only getting 0.5 volt out. So certainly not that flash down at 3 megahertz. And as I increase the frequency up to 9, it's not going to get much better there, and then dropping back down again up to, that's 20. So maximum transfer there, probably the wrong terminology but I'll use it, is around that sort of 10, 19, 11 megahertz. Probably something to go on there, I suspect, with the interwinding capacitance and the inductance and the like, but Obviously the coupling factor or the mutual inductance is varying there somewhat over that frequency range. So what I'm doing now is just take that out of circuit, and I'll give that a go just to see what difference there is. So again, just recapping, maximum is around that sort of 9, 10, 11, and then down at, there it goes, 3 megs, so just below the 80 meter band, it's not so good. So we're getting roughly, what's that, 0.75 volts peak to peak roughly. So let's disconnect that, and we can set that aside. Doesn't matter which side we go to because it's equal turns ratio, and hopefully if all goes well we'll have an output there. Right, so now we have, as you can see down there, that binocular core transformer in place of the ferrite rod. So we're now down at 3 megahertz there, and we can see there that half a volt peak to peak, 1-2 divisions, so 1 volt. So in other words, we're getting out approximately, pretty well on what we're getting in. And if we were now to increase the frequency, that's 9, 10, 11, 12, and then starting to drop off. So now up to, that's 20 megs, coming back down to 14 megs. 14 megs is still 1-2, roughly 2 divisions, so still that sort of what we're getting in is what we're getting out. So, arguably good performance across a much wider frequency range than what we would get out of this. I'm still going to go ahead and give this a go because I've got heaps of real estate on the actual circuit board to give that a go, and then see how it performs, and then I can always revert back to this particular transformer. So in terms of the actual configuration of the amplifier, I am going to use this arrangement. I totally acknowledge that these aluminium strips are more than likely inadequate for 50 watts, but I am going to give it a go. It will be interesting to see at what kind of sustained power this sort of aluminium heatsink would actually be useful for, noting that I do want to have, excuse me for leaning across the camera there, this fan mounted underneath. So there's going to be a little bit of clearance there, and air is going to be sucked up and then blown over those two there. So that is the plan, to have that. And again, I acknowledge that this is unconventional and not ideal, but like I say, I do want to give it a go because heat sinks are expensive. Not necessarily that difficult to get hold of, but they are quite expensive. So I am quite keen to see how well this will work, and up to what kind of power rating you could use something like this for. So the intent will be to have that our copper board mounted on top, and then our 2 devices on either side. Insulated, of course, because the tab here is connected to the drain. So it's going to be insulated, but the screw will have a metallic tab there, which I'll take off to be the output, and up here will be that output transformer. I'll probably have mounted down here slightly higher. We'll see how things work out, the biasing network. So that's the plan, and like I say, I'll just give it a go. It's cheap as chips to build, some bit of wood out in the garage, a couple of pieces of metal, and we'll see how that goes. And like I say, in fact I didn't say, drilling these holes, I just got a big drill out, had a file, so nothing spectacular to cut those out. So just, what's the word, sort of home handyman tools, nothing special to do this. Just a hacksaw to cut that. Anyway, so I'm going to say 73s there, and I think the plan now will be to solder this up. I have ordered some reparable IRF, the 24 ends from a local proper supplier, as opposed to using, for example, AliExpress. Point taken that I knew I was probably on a hiding to nothing by ordering 30 of these for $6, and as was quite rightly pointed out, more than likely these are either seconds, or they didn't meet the performance, or something else. We have seen down here that they do function, at least. They're not dead short or anything, but who knows when you start cranking up the power and the current through that. how well that would perform. So I think I might just wait until those other ones turn up. They're only a couple of days away, before actually mounting them on the heat sinks and giving it a go. But in between I can at least solder this up and get things ready to go. Anyway, I'll say 73's there. More than happy to accept and take in comments, but just bear in mind, I know it's unconventional, I know it's not the proper way of doing things, but hey, it's just what I want to try and give it a go and see what happens. Okay, cheers all, and we'll see you next time.